Hi folks, Mr. Long here. I'm going to do a screencast today on L'Hopital's rule, and it's a rule that I think most of you have heard about as you've gone through the calculus course. It's a rule for doing limits, and I wait until much later in the course to show you how it works because I think it's important that you know how to do limits using standard algebraic approaches because that will be an expectation for next year. Before, of course, I'll let you in on what L'Hopital's rule is, we need to understand why and how it works. Surprise, surprise. And so let's start looking through this. So what I entitled this part is can grade 9s do indeterminate limits? Yeah, they can. And just so we're consistent, what is an indeterminate limit? Well, it's a limit of the form 0 over 0, infinity over infinity. Another one is infinity minus infinity. 0 to the infinity. There's a few more. But certainly in this course, we focus on those two right there. Okay, 0 over 0, infinity over infinity. So what's happening? Well, let's take a look at this. So supposing I had you do that limit right there, 3x minus 6 over x minus 2. I'm pretty sure what you would do is, the first thing you would do is you would sub in 2 and see if, in fact, you have an indeterminate limit, right? So that's the first thing you would want to do. And so you would sub in 2. Let's zoom in on that a bit. So you'd sub in 2, and you would get, what would you get? 3 times 2 is 6, minus 6 is 0, and then 2 minus 2 is 0. So you have 0 over 0, it's indeterminate. Now, what we can do now, though, is we can rewrite this, we can factor it. What about the limit as x approaches 2 if I factor that out? 3 bracket x minus 2 over x minus 2. And now we can see quite clearly that x minus 2 and x minus 2 divide out, and our overall limit is 3. So that's a pretty straightforward limit. It's how we would have done it even in grade 11. We were simplifying rational expressions. We just didn't call it a limit. So, and that's a point discontinuity, right? At in this case 2 comma 3. So let's look at the graphs though of those, the numerator and the denominator, separately to see if we can start to understand why it behaves the way it does. So there's the denominator, there's the numerator. And what I've done is graph them, right? This is 3x minus 6. This one down here is x minus 2. And any grade 9 would be able to graph 3x minus 6 and x minus 2. So, because we spend so much time graphing those in grade 9. So let's take a look at what happens relative to this point here. And that's the location that causes 0 over 0. That's the indeterminate point. So what happens as I go to the right? So let's take a look at the y values. So notice they're starting out at the same spot. This one here has a slope of 3, and the green one has a slope of 1. And then what happens if I go out here? So I'm now at x equals 4, and I look at the two values that I have. So if I go to this spot here, and I'll do this in red, for this location here, when I have the numerator over the denominator, that's going to equal, well, that's worth, the numerator's worth 3, the denominator's worth 1, right? So that's 3 over 1. And then when I go out to x equals 4, the numerator over the denominator will be 6 over 2. And that's also 3. So why is it that I can just do the ratios of the y values and get my answer? Well, because they both diverge from 0 comma 0. One's going at a rate of 1, the other one's going at a rate of 3. So the ratio of the y values will always be 3 over 1. Why is that? Because the slopes of the two lines are 3 over 1. Right? The slopes of the two lines. This line here has a slope of 3. The other line has a slope of 1. We just divide out their slopes because they're linear. We wouldn't be able to do that if they were curved, of course, right? because that ratio wouldn't stay the same, right? So that ratio, if that's the axis, the ratio of those values are always going to be the same because they're linear. There's a constant rate of change. But if they're not linear, it won't be constant. So let's look at the next one. So if we were to simplify this, I think it would work out to be 6 over 2 would also end up being 3, I think. Yeah, so this one here is going to be the same. So that's, if I look at that and I compare it with that, and then I look at this the whole way here, and I compare it with that. So in the first one, I have 6 divided by 2, and that's worth 3. And then for this one, when I compare it at this point, I end up with this distance all the way is 12, and this distance from here to here up to the green line is the green line is, oh, whoops, what have we got here? 6x minus 6. And that's 3. Oh, 4. Sorry, folks. That's why I was looking at that. And that's also 3. Okay, so that means that the ratio of those two functions is also 3. 12 over 4, 6 over 2. Why is that? Because they're both linear. As I go to the right, away from that 0 over 0 location, the ratio of the numerator and the denominator is always going to be the same because they are linear. Okay, they are linear. Now, if we're looking at a point discontinuity, honestly, we don't really care what's happening far away from it, right? We don't care what's happening out here. We really care about what's happening here. And we know that it's going to be the same thing, right? If I did the ratio of the y values for the two functions there, it's still going to be 3, right? And if I went below, it's still going to be 3. So it just happens that it's linear, so it's always the same ratio. Let's do one more. Okay, let's do one more. So we're going to do 4x minus 12 over 3 minus x. Now, we know again for this one here, if we were to do this one, we would end up with 4 over negative 1, which would be negative 4, if we did that limit by factoring, etc. But how would the grade 9s approach it? Well, they would know that if they tried 0 over 0 in their calculator at x equals 3, they wouldn't get anything. It would just be error. But let's see what happens as I move away from that point. Is the ratio always going to be the same? Because they're linear. So then I go out to here, and I go to here. And so what is the y value? Because remember, the limit is the y value as you get really, really close. So as we get really, really close to x equals 3, what's the y value going to be? Okay, what will the y value be? We're not concerned with a limit at what's happening at 3. We're trying to figure out what is it when you get infinitely close to x equals 3. What's the y value then? So for this one here, when I'm at x equals 4, it looks like I've got 4 above negative 1. And here, I've got from here up to here is 8, and that's above, down here, that's negative 2. 4 over negative 1 equals negative 4. 8 over negative 2 is also negative 4. So the y value everywhere around that location is always going to be negative 4 because they're a ratio of linear relationships. Okay, so here, if I go to this one, then the ratios there are always going to be 3. Okay, as I get really close to that. It explodes at x equals 1 because it's 0 over 0, but everywhere else near it, it's going to be a y value of 3, a constant y value of 3. So we know that that's our limit value. As x gets really, really close to 1, y ends up being at 3. Okay, so now let's take a look. What happens if we come up with a scenario where we don't have a linear relationship? Whoops, I just want to go over here. So now I don't have a linear relationship anymore. Now what do I do? Right, so now I'm doing, the equation that I'm working with right now is, whoops-a-daisy, and I'll zoom in on that a bit. So we're doing x squared minus 9 over x minus 3. Now, what we would do, we know for this one, if we're going to do this limit algebraically, limit as x approaches 3, it'll be x minus 3, x plus 3 over x minus 3, right? And that would divide out, so that would just be the limit as x approaches 3 of x plus 3. And what would we end up with? 3 plus 3 is 6. So now I've graphed x squared minus 9 and I've graphed x minus 3 right there. And there's that point of discontinuity is caused by that 0 over 0 there. So that's the indeterminate part of that, right? So, and I should always check that. So what do I know about that? It's nonlinear, right? So it's not like I have straight lines to compare the slopes right here. But wait a second. We have a concept in calculus called local linearity. Maybe that will help us. So let's zoom in on that location right there. Okay, so we're trying to figure out what is the y value as we get really, really close to this point. We can't figure it out at that point because it's 0 over 0 there. Okay, we'll never be able to figure it out, but when we get close. So if you noticed, like 3.05, 3.1, we've zoomed in pretty close to 3. Well, if I look at this, what's going to happen here? Does it look linear now, though, when I get really close? Yeah, it has that idea of local linearity, right? And then, so what is the ratio of the y values? Because if it's got local linearity, the y value, when I get really close to there, has got to be a ratio of the y values, which is just a ratio of the slopes, right? Because it's the slope of this line divided by the slope of this line. And we can see that because they're linear, okay? If I know two equations are linear, it's just the ratios of their slopes. That's the big idea here. So let's look at some numbers. So I've got the y values put here. So that's 0.3025. That's 0.05. This one here is 0.61. That's the y value there. And whoops. And then I should do the y value there. By the way, this is the numerator part of the graph, and this is the denominator part of the graph. And that's at 0.1 is the y value there. So since they're linear, or at least locally they're linear, right? I can take that y value and divide by that y value, which is the same thing as dividing the slopes. What do I get? 0.3 over 0.05 is about 6. Okay, so 0.3025 over 0.05 is about 6. And this one here, 0.61 divided by 0.1 is about 6 again. Well, look at that. It appears that as I get really, really close to this location, that the y value of x squared minus 9 divided by x minus 3 is 6. How come I can do that? Because I zoomed in on it, and now it's got local linearity. So as I get really close to this 0 over 0, I can figure out what the y value is by dividing the slopes because I have local linearity. So what does that mean then? So the answer here, by the way, is 6, right? Which is what we figured out by doing it the long way. But if really close to this point here, I just divide the slopes because I have local linearity, will that give me an answer? Let's see if we can figure that out algebraically here. So let's try it. So that would mean that the limit as x approaches 3 of x squared minus 9 over x minus 3 is really just the limit as x approaches 3. When I'm getting really, really, really close to 3, it's just a ratio of the slopes, right? Because it's linear. So what's the derivative of the top? Because remember, I did them separately, right? I did the top and I did the bottom separately. So the derivative of the top, the slope of that top function is 2x. The one at the bottom is 1. Now, do I have 0 over 0 anymore? No, I don't have. This is not 0 anymore. So now it's 2 times 3, which is 6, over 1, which is 6. Right? So I'm just doing the ratio of the slopes because when I get really close, I have local linearity. Okay? And that's why I can do this. Okay? You can, as long as you can get a linear relationship between two functions that you're dividing, you're always going to know the y value because you just divide the slopes. Okay? So that's what L'Hopital's rule allows us to do. Here it is formally, and I'll maybe zoom in on that. So that's the formal. If you have any limit as x is approaching some value a, f of x over g of x, then, and if you have 0 over 0 or infinity over infinity, you have to check that. Then this is true. Okay, because what you're doing is you're zooming in on that indeterminate location, and even though like it might be a curve, it might be something that's quite curved, if you look locally, you're going to be getting two lines, right? If you zoom in. And then if you're zooming in, you can just do the ratio of the slopes, and that will always give you the y value as you get really close. Okay, notice that it's not the quotient rule. Okay, it's not the quotient rule. We do the slope of the top and we do the slope of the bottom. Then we divide them out. Okay, only then. All right, so this is just more information. These are going to be in your notes. Last thing I'll do is just a couple of examples. So here's the first one we're going to do. Ln x over x. Okay, so the first thing we should always do, and by the way, this is one going to infinity. So remember, our two forms are infinity over infinity or 0 over 0. So what is the ln of infinity over infinity? Well, it's nice to think of the graphs, right? So you know that that's what a long graph looks like. So as x goes to infinity, y goes to infinity. And y equals x is the same. It approaches infinity as well. So that's going to be an infinity over infinity. LHR means L'Hopital's rule. So I do need to check that it's infinity over infinity or 0 over 0. So what do I need to do if I use L'Hopital's rule? I do the derivative of the top, I do the derivative of the bottom, and I do them separately. And then I see if, and then every time after I do the derivative, I see, is it still indeterminate? Well, now the top has become 1 over x because that's the derivative of ln x, and the derivative of x is 1. So now, what is 1 here divided by infinity over 1? Well, 1 over infinity is 0. So I know that limit is worth 0 because 1 over infinity is 0. Okay, and I know that these are shown horizontally, which we don't normally do, but I think it's worthwhile to look at them normally, or look at them horizontally as much as you can. So let's look at another one. So this one here, sometimes you have to do L'Hopital's rule more than once. And this is an example where you have to use it more than once. So we've got a limit here. X is approaching 0. And e to the x minus 1 over cos x minus 1. And I should double check that that is right. E to the 0 is 1. Minus 0 minus 1. So that's 1 minus 1 on the top. The bottom, cos of 0 is 1 minus 1. So that is, in fact, 0 over 0. Okay, I've got that. So now I can apply L'Hopital's rule. What does L'Hopital's rule tell me I need to do? I need to take the derivative of the top. I need to take the derivative of the bottom separately because I know that the y value really close to that point of discontinuity is just going to be the ratio of the slopes. The derivative of e to the x is e to the x. The derivative of negative x is negative 1. The derivative of cos x is negative sine x, and the derivative of negative 1 is 0. What I do now, again, is I substitute in that 0. Is it still indeterminate? E to the 0 minus 1 over negative sine of 0. Well, if I check that, what am I going to get? E, any number to the exponent of 0 is 1, so that becomes 0 over 0. Well, now I can do the slope of the slope because the same properties apply. So I can't, it's still 0 over 0, so I have to do the derivative again. So now I do the derivative of the top. Well, what's the derivative of the top? E to the x minus 0. What's the derivative of the bottom? The derivative of negative sign is negative cos. And now what do? I substitute in again and see if it's still 0 over 0 or if I have an answer. So now that's going to be e to the 0 over negative cos of 0. And what does that equal? E to the 0 is 1 over negative 1. So your final answer is negative 1. Okay, folks? So again, do the derivative of the top, do the derivative of the bottom, and then and sometimes you're going to need to do some organizing algebraically, but hopefully that gives you an idea of the general approach to it, and it's a nice way to figure out limits of indeterminate forms. Okay, hopefully that helped.